Hello learners, today we are going to discuss the concept of isostasy. It is a little difficult to understand at times, but we are going to simplify the concept and see what it really means. So, what is isostasy? It is a geophysical phenomenon. It is not abstract, it is really happening. It describes the force of gravity acting on crustal materials of various densities. You know that the surface of the earth has materials of various densities. There are the thicker, denser oceanic crust and the lighter continental crust, which also has different materials on it, which have different densities. And this term applies to the principle of buoyancy or flotation to continents and oceans. Now, as we know that the crustal part of the lithosphere is actually floating on the asthenosphere, which is in a semi-liquid state. It is a plastic asthenosphere on which the crust is floating. Now, how we have mountains, how we have uprised, risen continental crusts and sunk the oceanic crust, that is important. So, let us just parse the term isostasy. So, the term comes from two Greek words, isos means equal and statis means stand still. So, how is the features on the surface of the earth or on the crust is standing at a particular condition? The concept of isostasy assumes a state of gravitational equilibrium between the lithosphere and the underlying asthenosphere. I just mentioned that the asthenosphere is a plastic layer on which that means it is not hard, it is not brittle, it is malleable, on which the lithosphere is floating. So, the crust is in a state of gravitational equilibrium between the lithosphere and underlying asthenosphere, so that the tectonic plates float at an elevation depending on their thickness and density. Isostasy helps to explain how different topographic heights can exist at the Earth's surface. When a certain area of the lithosphere reaches the state of isostasy, it is said to be in isostatic equilibrium. Isostasy answers certain questions. Is the deep earth rigid as a steel ball, or is it able to flow viscously like a sea of lava? What processes create the low standing oceans and the high standing continents? What forces hold up the mountains or conversely hold down the basins? What is the Earth's figure best represented at? Is it a sphere or a flattened ellipsoid? What causes the standard shorelines like the Scandinavian shorelines? How does measured gravity relate to the mode of compensation of the Earth's surface? How strong is compression, tension, shear in the Earth's crust and lithosphere? What are the rheologic laws that govern the deformation of the shallow and the deep portions of the planet? All these are questions of geology which try to understand how the different crustal shapes, the mountains, the plateaus, the plains and downthrust ocean bodies, oceans or ocean floors, how are they in such a condition and how have they remained in that kind of a condition? So, first in this figure we are looking at the concept. The concept, it is not possible to bring a mountain, I mean there are diagrams to show you the mountains and the crust, how to explain the concept, but this is a concept of isostasy explained with and without glacial ice. You see in the first diagram, in diagram A, there is glacial ice on the surface. The crust, what is happening to the crust? It is dipping at the center because of the pressure of the glacial ice, and the crust is moving away from the center. because that is the fluid asthenosphere which is moving away from each other. As soon as the glacial ice is removed, which is happening in a lot of places on the earth now, arrows you can see that the crust is trying to come back to its original position, and then ultimately it comes at its original position. In all the three images, the earth or the crust is trying to maintain some kind of an equilibrium because it has been depressed by the glacial ice. The lower portions of the crust, in the asthenosphere, it is moving away, that is below the crust. And when the ice is removed, the asthenosphere is bringing it back to the original position. Continental crust and oceanic crust exist on lithospheric plates, buoyant upon a molten, highly viscous asthenosphere. Within the Earth's crustal layers, balancing process takes place to account for different crustal densities and mass in crustal plates. Here in this diagram, we can see slumping of the crust into the plastic upper mantle, where the mantle, when it is depressing the mantle, the material, the plastic mantle, the material is flowing away from the center where the depression is. Under the mountain ranges, the crust slumps or bows deeper into the upper mantle. The mass is thinner across continental plains. This slumping results in a balance of buoyant forces. This is termed isostasy. Here, this is just an example to show how iceberg is floating on water, where about 9/10 of the iceberg is below the water and only the top of the iceberg is on the surface. Now, this is also a very, originally this was the idea that scientists had, that this is how the crustal matter was floating or depressing the upper mantle. But this is also something which was extremely erroneous. We'll be coming to that. The word isostasy was first used by the American geologist Clarence Edward Dutton in 1889. According to him, a state of balance must exist between the large upstanding areas of the Earth's surface, mountain ranges, plateaus, as well as continuous lowlands. He suggested that they may be compensated by lighter rock material beneath them, so the crust remains in mechanical stability on a rotating Earth. Another component is added, the rotating Earth. There is because of the centrifugal force which is created, there would be a tendency for material to go away, but that is not happening. Even before Dutton made his observations, the concept was put forward and relevant observations have been made by geodesists. Geodesists are those scientists who are measuring the Earth, the universe. So, the concept was put forward and relevant observations were made by geodesists. Astronomical determinations of latitudes were being made with reference to the vertical. The premise was that if the Earth was spherical and everywhere covered by oceans of equal depth, then the plumb line or the vertical would be perpendicular to the surface anywhere on the surface of the Earth. But the actual conditions are far more complex. The considerable protruding masses of lands, islands, mountains, plateaus and lowlands exert attracting forces which pull the plumb line away from the true vertical. All masses on the surface of the Earth, even you and me, the human beings, have gravitational pull. So, what is happening that this vertical or the plumb line in this case is attracted towards those masses, or it deflects the plumb line. This disturbing factor was discovered in 1859. Measurements were being taken in the Gangetic plains to determine latitude. It was in this process that this particular condition was discovered and tried to be some idea was given about it. Two places were chosen, their difference of latitude determined with the help of astronomical observations as well as geodetic survey and calculations. It was seen that the values differed appreciably. I mean, when there were calculated values and the other was actually observed values. Calculated values took the presence of the mountains as a factor which would deflect the plumb line towards it because it has its own gravitational pull. But the actual values were lesser. So, one of the two stations were within 100 miles of the Himalayan mountain ranges. It was presumed that the presence of this mountain range was responsible for deflecting the plumb line from the vertical, but it was not. The amount, the concept here is, or the problem here is that the calculated value and the observed value, there was a difference between the two. Deflection of the plumb line due to the presence of the mountains. Here we have two scholars, Airy and Pratt. Pratt was a clergyman, Airy was a geologist from the UK. They tried to explain why there was such a discrepancy between the observed and the actual calculated values of the deflection of the plumb line. The deflection of the plumb bob near the mountain chains is less than expected, that is from the observed values. Calculations show that the actual deflection may be explained if the excess mass is cancelled by an equal mass deficiency at great depth. I just showed you the picture of the iceberg. The iceberg is floating in water. 9/10 of the iceberg is below water, 1/10 is above water. But this is not the case of the mountains here. Here, the excess mass is cancelled by an equal mass deficiency at greater depth. This was the concept which was the result of this discrepancy in calculated and observed values. Here we have John Henry Pratt. He was one of the surveyors. He was a clergyman, as I told you before, a priest, an Anglican of Calcutta. He estimated the amount of attraction of the mountains and made allowance for in the measurement. He assumed that the mountain mass had an average density of 2.7, and he also noticed that the mountains did not exert as much attraction as it should have. This is Pratt's model of isostasy. Pratt gave probable explanation for this phenomenon. Either the mountains did not have their supposed density, they were exceptionally light, low density due to the expansion of the crust that was heated kept its volume at the expense of its density, volume at the expense of its density. So, they were high, but they were lighter, they were less dense. So, this was what he was trying to explain. Excess of matter they represented was compensated for deficiency of density below the surface. Here you can see in this diagram that these vertical columns, they end at particular, the blue patch shows that they end there, that is the level of compensation, which is the same whether it is a mountain or whether it is an ocean basin or whether it is a plain or whatever. Then we have George Biddle Airy. He was an astronomer royal and a geologist also. This is the model that was given by Airy. Here you can see that he does not talk about a level of compensation. He says that each of the density remains the same. Airy was a contemporary of Pratt and he postulated his own hypothesis. There were similarities and there were differences. He assumed that the continents and the islands are resting on or floating in denser areas and that the excess of matter above the upper substratum is balanced by deep projections of the light material into the substratum. Instead of ending at a particular level, the level of compensation, the longer or the bigger structures, bigger relief structures are penetrating more into the substratum, while the density remains the same. That is, the thicker part of the crust sinks down into the mantle while the thinner part floats on it. This hypothesis also describes the Earth's crust as a rigid shell that floats on the mantle, which is denser than the crust despite being viscous. Airy accepted Pratt's assumptions that the Himalayas floated on a denser substratum, but did not accept the fact that the Himalayas were of a different density than the plains. So, the basic assumptions between Airy and Pratt is Pratt talks about difference in the densities. Bigger the relief feature, lower the density. But Airy talks about similar density, bigger the relief feature, it is sunk more into the substratum, and the smaller it is floating towards the surface. He explained his theory in terms of varying thickness and lengths. See, here is a comparison of Airy and Pratt's models of isostasy. First is Pratt's model, and then we have Airy's model. There was a big debate in 1855 after a British gravity geodetic survey in India. Pratt suggested that the mountains do not have roots, but instead the topography is compensated by less dense, therefore lighter block, and that all topography was compensated at the same depth. That is the level of compensation, approximately about 100 kilometers below the surface. That was an estimate. Mr. Airy suggested that the mountains had thick, low-density roots supporting mountains, and that the depth of compensation was not constant, but the density of the blocks were constant. Now, who was correct? Airy was mostly correct about what supports the large mountains, but it took until the 1970s to prove this particular concept. But Pratt was correct in the difference between the low standing ocean basins and the high standing mountains. Then we come to Hayford and Bowie. Hayford and Bowie in early 20th century, the first half of the 20th century, they were American geodesists. They were able to prove that anomalies in gravity relate directly to topographic features. This validated the idea of isostasy. They further established the concept of the depth of isostatic compensation. Both were extensively on isostasy and geodesy. Hayford was the first to estimate the depth of isostatic compensation and to establish that the Earth is an oblate spheroid rather than a sphere. Then we come to a concept of gravity anomaly. For quite some time, scientists were not certain as to how to account for the difference in values between calculated values of gravity and actual values. This is what we found, that there was an anomaly between the gravitational pull of the plumb line towards the mountains, between the calculated and the actual. The practical problem was to bring both the values to agreement. Solution was difficult. There was no direct method of observation possible, as the reason for the anomaly lay deep between the surface of the Earth. Scientists of the US Coast and Geodetic Survey under Hayford and Bowie undertook this task. Hayford assumed that there was a level below the Earth's surface, which he called the level of compensation. This was similar to Pratt's concept, below which densities were uniform and above which the effective variations of densities were supposed to exist. To calculate, they devised a formula. Here we have the level of compensation. This is according to Hayford and Bowie. I haven't mentioned the formula here, it will complicate things unnecessarily, but you can see there is a level of compensation which about 100 kilometers below the surface. Ocean and the continental crust, you can see both of them are there, and both of them have their center of mass. The oceanic is at a lower level because it is thicker and it is not that high, and continental at a higher level. For contiguous columns of equal cross sections based on the level of compensation, density was inversely proportional to height. This also is according to Pratt's concept that the bigger the relief body, lesser the density. From the figure, the assumption was that the varying volume of matter in different columns is compensated by their density. This is referring to the previous slide, so that they exert equal downward pressure. At the level of compensation, thus balancing each other, this theory was considered satisfying as it substantiated the equal standing concept of isostasy. But such an explanation depended on the assumed depth of the level of compensation, which cannot be measured. It has also been pointed out that there are infinite number of conditions, that is, only one condition probably does not explain the gravity anomalies. Also, there are definite evidences that density variations do not extend below a certain depth. Therefore, the causes for the anomalies are located in the outer crust rather than beneath it. One of the reasons for this is, after a particular level, it is the upper mantle, and in the upper mantle, the densities, because of the characteristic of the upper mantle, the heat and the plasticity in the asthenosphere, density variations are not possible. So, Hayford assumed that the level of compensation to be at a depth of 100 kilometers from the surface. This is an assumption, calculated, but it's not proven fact, but whatever. Then we have Heiskanen, even a much more contemporary scholar. Another hypothesis was developed by the Finnish scientist Heiskanen. His ideas were a compromise between Pratt and Airy's hypothesis, but favoring Airy's ideas more. Interestingly, the Hayford-Bowie concepts favored Pratt's ideas and Heiskanen favored Airy's hypothesis, that all material, crustal material, had approximately the same density. It depends on the size as to how much it has gone slumped into the upper mantle. Then we have Wenning Menes. He was Dutch geophysicist and geodesist. He is known for his invention of a precise method of measuring gravity. Thanks to his invention, it became possible to measure gravity at sea, which led him to the discovery of gravity anomalies above the ocean floor. He later attributed these anomalies to continental drift. In this, Menes said that the lithosphere acts as an elastic plate. Its inherent rigidity distributes topographical loads on a broad region by bending. This hypothesis was suggested to explain how large topographical features like seamounts could be compensated by regional rather than local displacement of the lithosphere. Very often, when we have a seamount or a coastal mountain chain, just after that there would be an area where there would be a linear depression, like the trenches. Here, the local and regional compensation, you have the local compensation here on the right side of the diagram, and the first one is regional compensation, where the compensation is not exactly below where the pressure is created, but it is to the side of it. And in the second one, where there is local compensation, the pressure, the body which is pressuring it has displaced part of the crust into the asthenosphere. Deposition, erosion and isostasy. When large amounts of sediments are deposited in a particular region, the immense weight of the new sediments may cause the crust below to sink. This is how geosynclines are created. I'll just come to this particular point. Similarly, when large amounts of material get eroded away from a region, land may rise to compensate. This is what is happening in the Himalayan area. It is said that it is not said, it is a known fact that the Himalayan mountains are rising. This is because a lot of erosion is going on from the Himalayan mountains to the plains. Therefore, a mountain range is eroded down and the reduced range rebounds upward to a certain extent. That's why we say that the Himalayas are rising and erosion starts once more. Now we are talking about the Himalayas rising, but what about the Indo-Gangetic Plain? This is a huge geosynclines. You must have studied about geosynclines, where the material which is coming from the Himalayas are deposited, and it is causing the crust to sink. There would be a time the crust can't sink anymore, it is going to rise, and then would be a second parallel mountain range formed. I mean, I can just, because it's a geosyncline, it is depressing, and it can, at some point of time, it will rise as a mountain range. Some of the rock strata now visible at the ground surface may have been at great depth below the surface, buried under other strata, to be eventually exposed as those other rocks are eroded away and lower layers rebound upward again. If you see the picture of Kailash Parvat, which is supposed to be inaccessible, nobody can climb it, it is actually a synclinal feature. It was at a level much lower than what it is now, and it has risen. This was because of erosion and because the Himalayas are rising. This is what the situation is. So, some of the rock strata now visible at the ground surface may have been at great depth below the surface, buried under other strata, to be eventually exposed as those other rocks are eroded away and lower layers rebound upward again. When sediments brought down from the mountains are deposited on the bordering plains, the crust below sinks. This is called a geosyncline. I just mentioned it 2 minutes before. The Indo-Gangetic Plain is such a geosyncline. The geosyncline also sinks to a certain depth before it rises and raises the sediments along with it and gives birth to a new mountain range. Just to mention, you all know about the Tethys. The Tethys was a geosyncline, and material from both sides of the continents were brought in, and ultimately they were crushed and to form the Himalayan mountain range. Concept of isostatic rebound. If the concept of a floating crust is correct, one would assume that large topographic changes such as the removal of a mountain range by erosion or by deposition and subsequent melting of large ice sheets lead to isostatic adjustment of the Earth's crust. Removal of a large load should cause the crust to float up higher, while loading of crustal rocks should make the crust sink deeper. Isostatic rebound has been observed for many formerly glaciated locations. Here we have the isostatic rebound along the Norwegian coast. One particular evidence of isostatic rebound is that of emergent coastlines, where the previous coastline would be at a level much higher than what it is, the coastline is at the particular point. Today, with the glaciers gone and land surface is still rising in some parts of the world, one of the best examples come from Scandinavia, which is still rebounding from the last ice age. As a result of isostatic rebound, it is often possible to see old shorelines that formed at the end of the glaciation, when the land surface was still depressed. Today, there are many meters above the present sea level. There's another area of isostatic rebound. Most of the areas in the northern hemisphere which are bordering the Arctic Sea or the higher latitudes, we have examples of isostatic rebound. This is north of Canada, the Hudson Bay. Formation of ice sheets on cause Earth's surface to sink. This was the first example that I had given about isostasy. What is isostasy? How, to explain the concept of isostasy. On the other hand, in the post-glacial period, isostatic rebound is observed in areas covered with ice sheets which have now melted, such as around the Hudson Bay. As I told you, it's northern Canada. As the ice sheets melt, the load on the lithosphere and atmosphere is reduced and they rebound back to their equilibrium level. There is always constantly isostatic equilibrium. Is the earth is trying to gain isostatic equilibrium, whether it is the geosynclines, whether the Indo-Gangetic plain, whether it is the Himalayas, or whether these northern parts of the earth where glaciers have melted and the earth surface is the land surface is rebounding to its original pre-glacial condition. Thank you.